So, as we continue on with section 3, looking at applications of derivative, we get to section 4, concavity and the second derivative test. Yeah, if the first derivative test was fun, the second derivative test must be even better, right? Okay, so our objectives for this unit are determine intervals on which the function is concave up or concave down. Find points of inflection of a function and apply the second derivative test. So of course we're going to have to define what does it mean concave upward, concave downward, and what an inflection point is. So let's start with concavity. And let's switch over here. You might remember from your science classes, this idea of concave. We talk about with lenses, so I'm just going to take a look at this for a second. When we look at lenses, we talk about concave or convex. And a convex lens is one that looks like that, and a concave lens is one that looks like this. And I always was taught, and the way I remember it is concave means it kind of looks like a cave mouth. And convex is kind of the opposite of that. You notice they both have the same basic curve in it. It's just one's point kind of popping up like this, one's kind of inset. Because we're dealing with a physical lens, so we're dealing with this part of it when you're dealing with it in physics and in your science classes. But mathematically, we're just interested in this curve, and this curve can look pretty much the same whether we're talking about convex or concave. So we just use the word concavity because that's the one that makes a little bit more sense to me, at least. And we talk about concave upward, where the mouth of the cave, if you want to think of it that way, is pointing up, and concave down is where it's pointing down. We don't have a lens to determine what side of this we're on, so we can't talk about the concave or convex. But that's really what we're talking about, that. So when you hear concavity, if you remember lenses, that might help you think about that a little bit more. But if we look at this curve here, we're concave down at this part of the graph, because this graph kind of think again, looks kind of like that parabola type shape, not exactly, but it's pointing down. At this point here, we're flipping and we're going concave upward. And we're going to talk on the next slide. This graph right here, you notice this is the first derivative. And how does the first derivative apply? You notice here, this point is where the first derivative is 0. Again, hey, we looked at that with the first derivative test. Said that where the first derivative is 0 is where we can have a possible extrema. First derivative is 0, we can have that. On this point where it's concave upward, we can see the first derivative is always increasing. And here where it's concave downward, the first derivative is always decreasing. So those are kind of the ideas we're going to put together as we look at this section. We're pretty much, that's the gist of this lesson. Now we're going to get into the details of what we're going to do with that. So our test for concavity, we're going to say f is a function whose second derivative exists. And we're looking at the second derivative is positive for concave upward. Second derivative is negative for concave downward. Let's go back to this one. If the second derivative is basically talking about whether the first derivative is increasing or decreasing. So when I say here, did I get rid of that? The first derivative is decreasing. That means that the rate of change, or the second derivative, has to be negative. Because again, when we said when the rate of change is negative, it's decreasing. So here, when this function is increasing, its rate of change is negative, or is positive, increasing. Here it's decreasing, so the rate of change is negative. So that was that first derivative test. So that's basically what we're saying. If where this is concave upward, you notice all of this, the first derivative is increasing, so that means the second derivative, which is saying how it's changing, is going to be positive. So that's that idea we're working with, why we go to the second derivative on this. So that's where this test for concavity comes for. We're looking at the second derivative. And again, where does that change from, the second derivative change from positive to negative? It's going to be where second derivative is 0. So let's look and do one of these problems. For some reason, I decided to give you really nasty problems to work with on these first two. So we're just kind of going to work through this one. I'm going to want more room. So, I don't need this. Let's start with our problem. It says f of x equals 6 over x squared plus 3. And we said to determine the concavity, we want to figure out the second derivative. When I work through this, I'm going to make this 6 times x squared plus 3 to the negative 1, because I don't want to use the quotient rule. Here this is a constant multiple, so I can just go through and, oops, not hit that button. I gotta get used to the right buttons to hit, right? You think I'd have it figured out by now, right? The first derivative, is going to be 6 times the derivative of this, which is going to be negative 1 times x squared plus 3 to the negative 2, times the derivative of x squared plus 3, because this is, again, it's a composite function. We got to chain rule it. So we got 6, a negative times negative 1 times 2, so we get a negative 12x times x squared plus 3 to the negative 2, or negative 12x over x squared plus 3 quantity squared. Would be fine if all we needed was the first derivative, but no, that's not good enough. I need the second derivative. So you can either use this form and use the product rule, use this row form and use the quotient rule. I don't know. They're both about as painful as the other. So I'm going to use this one and use the product rule, because if I can avoid the quotient rule, I will. So we're going to take the first times the derivative of the second. And again, this is a chain rule as well, or general power rule. So we're going to go negative 2 times x squared plus 3 to the negative third times the derivative of x squared plus 3. And then we add to that, because no, we're not done with it yet. We got to add the derivative of the first part, which is a negative 12, times the second part, x squared plus 3 to the negative 2. At least I don't have to chain rule that part of it. So, where does this take us? We got a negative 12x times negative 2 makes it positive 24x times a 2, which would be a 48x squared times x squared plus 3 to the negative 3. And then I'm minus 12 times x squared plus 3 to the negative 2. Now, I'm going to take this back to fraction form because it might be a little easier to combine those. 48x squared plus 3 cubed, 12 x squared plus 3 squared. So you see, if I want a common denominator to combine those, I have to take this times an x squared plus 3. So I get the second derivative equals 48x squared minus 12x squared minus 36 all over x squared plus 3 to the third power. Which is going to be 36x squared minus 36 over x squared plus 3 cubed, or 36 times x squared minus 1 over x squared plus 3 to the third power. Yeah, okay. So my second derivative was 36 times x squared minus 1 over x squared plus 3 cubed. Now our goal is we're looking for concavity. So we want to look where the second derivative is positive or negative. So where it's going to switch is where the second derivative is 0. So if we want to look at 0 equals 36x squared minus 1, x squared plus 3 cubed, we first can be thankful denominator will never be 0, so I don't have to worry about asymptotes. So I only have to worry about when does the numerator equal 0, and that's right here, x squared minus 1. So this is going to be x equals 1 or x equals negative 1. Those are the points where the second derivative is 0, so those are the points where it can switch between positive and negative. So we come along and set up our intervals. Negative infinity to 1 to negative 1, negative 1 to positive 1, positive 1 to infinity. And we have to look at the second derivative and see is it positive or negative at each one of those. So we're going to do what we did with first derivative. If we put in a negative number, if you look at this, the denominator is always going to be positive. Because any number squared is positive plus 3 is positive. The numerator, if this number is less than negative 1, let's say negative 5 squared is 25, so this is going to be positive over positive. So this is greater than 0, so this is going to be concave up. When we look at between negative 1 and 1, we're going to just look at f of 0. F of 0, we can just kind of inspect this and say, oh, we got 36 times a negative 1. That's going to be negative because this is going to be negative at 0. This is always going to be positive, so it's negative over positive. So that's negative. This is concave down. Last one, when we look f of 5, we look bigger than 1. Again, bigger than 1, this is going to be positive. Denominator is always positive. This is going to be positive. We're concave up. So this is this whole process of determining concavity. And it's as hard or as easy as finding the second derivative. So I'm going to give you this one to try. So again, it's a quotient rule problem. This one we can't avoid the quotient rule. You're going to have to do that. But pause the video, give this a try, see if you can do this on your own. And I will then start it up again and see what I got. Oops, I did that again. F of x equals x squared plus 1 over x squared minus 4. First derivative, we're going to use the quotient rule, so we're going to go x squared minus 4 times the derivative of x squared plus 1 minus x squared plus x squared plus 1 times the derivative of the denominator, 2x, all over x squared minus 4 quantity squared. And see what we can simplify. We get 2x cubed minus 8x minus 2x cubed minus 2x over x squared minus 4 squared. And yay, those cancel out. And I'm left with my first derivative is just a negative 10x over x squared minus 4 squared. That one wasn't too bad. Now let's go to our second derivative. So we go x squared minus 4 squared times the derivative of the top minus the top times the derivative of the bottom. Don't forget, that's a chain rule. 2 times x squared minus 4 to the first power times the derivative, 2x. All of this is over x squared minus 4 now to the fourth power. Before I go too hog wild here, let's take a look at this. We got a negative 10 times x squared minus 4 squared minus a negative, so we'll go plus. 10 times 2 is 40 x squared times x squared minus 4 over x squared minus 4 to the fourth power. And look, we got an x minus 4, x squared minus 4, x squared minus 4. We can factor one of those out, so I don't have to square it there. So I got negative 10 times x squared minus 4 is negative 10x squared. Negative 10 times negative 4 is 40, plus 40x squared, all over x squared minus 4 cubed. So I get 30x squared plus 40 x squared minus 4 cubed is going to be 10 times 3x plus 4 divided by x squared minus 4 cubed. Now, we look here. If we look at the very original function, right here we have x cannot equal 2 or negative 2. Those are going to be vertical asymptotes. So when we're looking, that basically already breaks up my function into negative infinity to negative 2, negative 2 to 2, 2 to infinity. We just have to see at the second derivative, are there any other places where we could break that up? But if we look here, this will never be 0. Or wait. Sorry. Oh, that's a squared. This can never be 0 because this will always be positive. So our only possible places are where the second derivative doesn't exist. So we already have that broken up. If we knew this, why did we do the second derivative? Because we're using the second derivative to find concavity. So we still needed to go through all that hassle, right? So to determine concavity, we're going to look at our negative infinity to negative 2, our negative 2 to 2, and our 2 to infinity. And we're going to check the second derivative. So if we go less than here, well, if we think about a number, again, I'm going to look here. The numerator is always going to be positive. Denominator, if we have like negative 5 squared is 25, this is going to be positive to the third power is positive, so this is greater than 0. This is concave up. If we try f, the second derivative at 0, again, the numerator is always going to be positive. Denominator, this is a negative number to the third power is negative. So this is less than 0. It's concave down. And I always draw these little pictures to help me remember and keep straight what's going on. And again, here, if we go second derivative at 5, again, the numerator is always going to be positive. And again, this is bigger than 4, so that's going to be positive. So this is, again, concave up. I'd suggest as you're doing these problems, when you get done with it, grab your calculator, grab decimals, graph the original equation, and see if what you came up with looks right. So we can double check ourselves here. So basically looking at this concave up, concave down is like we're looking at, is it increasing or decreasing, except we got to add that extra complexity of finding the second derivative. Now, come to this points of inflection. Actually, I'm going to stop this video right now. It's 24 minutes. I'm going to do a second video for this one to pick up and do the second half of this section. So we'll see you in the next video.